gear, hat, glasses, text, flame retardant uniform, the works. There are 3 places we will need to check: the conveyor belt motor, the power to the lift motor, and the power to the robot.
You mean Calibot, right?
Right, sorry. Calibot. I'll watch to make sure we have the right fuses. You will do the actual testing. You will also record the results on your worksheet. Take the black lead of the meter and hold it against the bottom of the conveyor belt 2 fuse, or the load side. The load side is where the power is coming from. Now take the red lead of the meter and hold it against the top of the conveyor belt 2 fuse, and then read the meter. Record on your worksheet what voltage you have showing on the meter. The meter should read close to 0 if we have a good fuse. If it is bad, it would show close to 480 volts going in and nothing coming out. Now repeat that process for the robot's fuse. Record your results. One more to check. See if the lift motor fuse is working. Okay, do we have a faulty fuse? I agree. There doesn't appear to be anything wrong with power flow to the motors on the line. Operator error is a possibility we need to check. Let's ask Haley some questions. Haley, you said you didn't get any error messages from Calibot. Thanks for checking that. Did you also check the calibration this morning? Could the calibration be far enough off to be causing the line to stop?
No, I don't think that could be it. We manually tested her calibration and everything checked out. I think it must be something else causing the problem.
Good to know. Was Calibot in the correct home starting position when you started the line moving?
Yes, I even double-checked. Wouldn't want to hurt or confuse Calibot.
Okay, we've eliminated a bunch of reasons why the line might have stopped. There are just 2 left: the timing of the line itself and the limit switch. The timing refers to the amount of time each section or moving part of the line takes to work. The timing of all the sections is set very carefully so that everything will work together. Let's say that the lift is late moving down and there is already an engine block moving towards it. That engine block could get jammed under the lift or fall on the floor. We need to check 2 areas to determine if the timing is working as expected. The amount of time it takes the Calibot to finish measuring the engine block, and the amount of time it takes for the lift cycle. To check the timing of the robot measuring the block, we need to look at the ladder logic. Ladder logic is a programming language that represents the various motors, switches, and robots on the line in a graphical way. Here is the ladder logic screen for this section of the line. It looks complicated, but basically it's just a way to show what happens on the line. And in this case, it helps with troubleshooting. Ladder logic is a Boolean system, which basically just means everything is true or false. Looking at these first 2 lines, if limit switch 1 is activated or true, then that means the engine block is there to be measured, so the robot begins measuring. On the second line, if it is true that the measuring has started and the measuring is good, or the measurements are what they should be, and limit switch 1 is activated and limit switch 2 is not activated or not true, then conveyor 1 will begin moving. You'll get used to reading one of these pretty quick. For now, I'll show you what you need to know to get the line back up and running. To figure out the time it takes for the robot to measure the engine block, just look at where that happens on the ladder logic. That 36 seconds shows us what the timing should be for that measurement. We just click on that timing to get a readout of what is actually happening. This is the readout of what was happening. Take a look at the screen. Is an engine block being measured every 36 seconds? So, there is no timing problem there with the robot. The other possible timing issue is the movement of the lift. In order to pick up the engine block smoothly, it should also cycle through its movements up and down in 36 seconds. However, figuring out if it is doing that takes a bit more effort than just checking the ladder logic screen. We need to understand the sequence of steps the engine block goes through to get to the next section of the manufacturing line. The engine block is transferred into the lift by the block transfer motor. The lift travels up to the next section of the line. The engine block is transferred out onto the conveyor that is the next section of the line by the block transfer motor. The lift travels back down to pick up another engine, starting the cycle over again. In order to figure out if the timing is correct, we have to use what I hope is the best equipment in this plant, our brains. We have to calculate if the lift is taking a total of 36 seconds to go through its cycle and then confirm that it is actually doing what it's supposed to do. So, just going by the timings on the ladder logic, there are 2 times the engine block is moved by the transfer motor on and off the lift. And 2 times the lift moves up and down. Does all that add up to 36 seconds? All right, good. But just because it's supposed to be taking 36 seconds to go through the cycle doesn't mean it actually is. So we're going to have to check the timings for each of those movements too. Here's a screen that shows the timings for the whole cycle, one movement at a time. It's important to understand that these times are the start of each movement. By looking at when each movement started, we can determine how long the movements took. Study that for a bit and record the times between each movement on your worksheet. Now look across the columns of your worksheet. Does that add up to 36 seconds? Okay, there aren't any issues with timing, so that just leaves the limit switch the engine passes on its way onto the lift. You probably need to know more about what limit switches do. They basically turn power on and off if a particular situation is true. For example, they can indicate if a part is in the right place for the robot arms to work on, or if the part is in the right place to go up in the lift safely. They're even used to determine if an object has passed, like if the lift has passed a certain point and should start slowing down. Take a look at this diagram. The arm of the switch can be positioned in 90-degree increments, depending on what you want it to do. Here's how this is supposed to work. When an engine block moves past this first limit switch here, the block pushes the actuator arm from an upright position to the right toward the lift. The switch then signals to the computer that the engine block is in the right place and ready to move onto the lift. There are 2 other limit switches associated with the lift. The lift platform pushes one actuator arm down when it travels all the way to the bottom of the shaft. The switch then sends the signal that the lift is in place and ready to receive the engine block. The other switch is activated when the engine block is on the lift, pushing the arm down when the block is in place and ready to go up. I really hope it's not one of those 2 switches, because they're a lot harder to get to and test. Cross your fingers and let's look at the limit switch before the block goes onto the lift. Take another look at that ladder logic screen to see what it says about that limit switch. Aha! You can see here that limit switch 3 is inactive because there is no light behind it, thus proving my hypothesis and costing